Good morning, everyone, and thanks for coming to my talk in the early morning. And before my talk, I'd like to take this opportunity to thank the Newton Institute for organizing such a great workshop and also inviting me to be here to share my work with you. Okay, so the theme of the workshop is scalable statistical inferences. So I'm going to talk about how do we do interaction selection and by developing some new scalable algorithm and statistical methods. This is still ongoing work. So actually my talk today is based on 4 different papers over the last 3 years. Okay, so all of them have been either published or accepted. So you can always check archives for details. Today I just like to give you a summary about our discovery and where we are now. Okay, so let's start with the simple linear regression models where we like to find the relationship between the output y and the multiple regression predictors x. Okay, and but we know this main effect only model can be restrictive in practice for some very complex problems. So here I give you several scenarios where the interaction actually can play a very important roles for model interpretation and also improve the model prediction. And one popular, actually, one very hot area on this topic is GWAS studies, where we like to find out the gene-genes interactions or how the gene interact with environments, okay, like our bodies. And genes and the genes in our body and our life habit and or like other clinical measures. And in the disease studies, and there has been a strong belief that the behavior of a person and the exposure to environment, they work together on the disease occurrence rate. For example, like in 1992, it has been discovered that smoking works with exposure to the airborne pollutant altogether in a nonlinear fashion to increase the rate of lung cancer. Okay, they are not just work on this lung cancer separately. They work together in a very complicated nonlinear fashion. And also in sociology, it has been believed that the politics and economics goes interact together. And so anyway, we have a lot of motivations for doing interactions. So let's look at the simple way of considering linear interactions in linear regressions. Okay, so basically we just include all the quadratic terms. Okay, and so when you look at this model, it's still linear basically, and one dimension p is low. It's not that problem. The problem is really when p is really high, then we have a lot of challenges, including computational challenges. First of all, the number of parameters is now it's at level of a p squared. Okay, so now if we have 10,000 variables, then the number of parameters is up to 10 to the 0.8 scale. And if p is even high for exponentially high of a sample size, and then it's just we have a very serious problem of cursive dimensionality. And if here I'm only considering 2-way interactions, if we extend this to 3-way or higher k-way interactions, the number of parameters even go higher quickly. Okay, so we have a problem of to install this huge design matrix as we do in standard linear regression. Usually we put the design matrix x. Now the matrix has to be x squared, and so on. So it's impossible to even store or operate this design matrix for high dimension problems. And for theoretical problems, you want to study the asymptotic behavior of model selection for this model. Okay, then we have to deal with the behavior of interactions. And the behavior of interactions actually, they have a much heavier tails than the main effects. Okay, if we assume X has a Gaussian assumption, then this interaction effect will not have a Gaussian anymore. Okay, so tails are heavier, and also if you look at the design matrix, which contains main effects and interactions, there will be very strong correlation between main effects and interactions. So that will also cause problems of estimation, stability, and so on. And one key issue, actually there are two key issues we should follow when we do variable selection or model selection for this model. So naturally we will say, oh, the dimension is so high, we should just reduce dimensionality by doing some variable selection techniques. Okay, and so there is a very natural hierarchical structure in this model. Okay, so we have interactions and appearance, and we have main effects. So for example, we can say xj, xk, they are two parents of the interaction product xj, xk. And on the other hand, xj, xk is a child of the main effects. Okay, and so when we do variable selection, we have to bear in mind these hierarchical structures. Actually, this is not new. Back in 1977, Nelder actually suggested this marginality principle. Okay, so he actually advocated when you do variable selection, you have to follow this principle. Like you have to select parents before you select the children. Okay, so parents has to go into model first before the child. Okay, and so later on, there actually is also a lot of follow-up work, like including in 1989, McLaw and Nelder, they actually they emphasize this marginality principles. Okay, and so we have to actually, when do variable selection, we have to make sure we have to follow that actually principle. Another principle is like invariance principle. Okay, and the very actually tricky thing about this interaction, this quadratic regression model is if you do linear transformation of this x, okay, for example, xj minus constant and multiplied by a constant, then actually the variable, the structure of the model will change. You can do a linear transformation to make a main effects either positive or negative or even disappear. Okay, the problem is like this model is really tricky, and you have to make sure you do linear transformation properly. So this is another principle we call it's invariance principle. We will have to make sure our procedure actually will identify the correct model, okay, on any linear transformation, or linear transformation here, basically location and scale transformation, okay. And this is where I'm going to define the concept of important terms, okay. So when we look at this model, okay, and how do we decide which predictors are important, okay. In the linear models, we just look at the regression coefficients, beta j's or beta jk's, and to check their sign. Okay, if their sign is 0, then they are not important. Otherwise, it's important. It turns out this definition is not valid anymore because of this linear transformation that can change the model structure easily. So I'm going to define a proper definition for what are important main effects and what are more important interaction effects. Okay, so hopefully, yeah. One more thing about this hierarchy, this marginality principle, we actually can formulate this into the heredity conditions. Okay, so we have actually strong heredity conditions. Essentially, it says before you select interaction term, both parents have to be in the model already. And or we can have a weak heredity condition, which requires at least one parent in the model before you select the child. Okay, so we are going to actually, we are trying to follow this, trying to propose procedures which actually obey these conditions. Okay, so that's basically motivation of interaction selection work and its main issues and the challenges. So what are the existing work in the literature? And so actually, we have a naive approach, okay, which just ignore hierarchical structure. And for example, we can do naive LASSO, okay. We just put this huge linear model, okay, and then put penalty on all the regression coefficients for linear terms and also main effects and interaction terms. We call this flat model, okay. It treats the main effects interactions equally, totally ignore the hierarchical structure, and so it does not guarantee the model hierarchy. So that's a naive approach, and it is not actually desirable because it does not follow this model hierarchy assumption. And then there are some classical low-dimensional methods based on forward and backward, and which works under marginality principle, but it does not. It's not scalable for high-dimensional data. And recently, after the LASSO has been proposed, and there are some researchers trying to generalize LASSO to this interaction selection, and there are 3 papers on this in 2009 and 11. Okay, so they are trying to design a special, actually kind of constraint, okay, to enforce the hierarchical conditions. Okay, so here I give you one example of this work. It's called the Shin by Choi, Lee, and Zhu. I mean, Zhu is Ji Zhu in Michigan. So basically, the idea is they want to actually enforce these strong hierarchical conditions. So they actually put actually a relation that the beta jk, that's main interaction, and they express this beta jk in the terms of a product of main effects, beta j, beta k, and gamma jk. So they use this reparametrization to link the interaction coefficients and the main effects coefficients. And then they actually fit this LASSO regression subject to this reparametrization constraint. And actually, this method, I'm going to give a comment about this method. Okay, the paper actually talked about how do I compute these optimization problems and what are the theoretical properties. Okay, so the advantages of this method is it keeps the model hierarchy. That's good. And secondly, it can show the hierarchical properties, and its performance is pretty good for moderate p. Okay, everything is great. But there actually are some like computational issues for this technique when we deal with large p. First of all, this optimization problem is not convex. Okay, so it does not converge to global and unique solution. So that's problem 1. And also you need a very special programming techniques to handle this kind of a constraint, and which makes the computation very expensive. In the paper, they showed the largest P they can handle is like 200 variables, 250 variables. That's what they do. And also, when you implement this procedure, you need actually you need a big computer to store all this P squared P squared by n design matrix. Okay, so it's good for moderate P, but I'm not going to say it's really scalable. Okay, and very recently, actually, besides our work, there are also other groups working on interaction screening, and this tool actually works for interaction screening, and yeah. Okay, so next I'm going to talk about our works. Okay, so the goal of our works are trying to develop some scalable algorithms for interaction selection. Hopefully it can handle ultra high dimensional data when P is much larger than N. And we want to enforce these hierarchical principles in a cheap way. We don't want to do very expensive constrained optimization. And also we want the algorithm to be efficient in P, So ideally, if the algorithm is linear in P, that would be great. And also, we don't want to store the whole design matrix based on the expanded interactions. And last thing we want is theoretical properties. Hopefully, this procedure is not heuristic. You can have some theoretical support for these techniques. And also, empirically, they should perform competitively. Okay. So, as I mentioned at the beginning of the talk, actually, I'm going to talk about multiple papers here. So, we actually have proposed two new class of methods. The first class is based on forward selection. Okay. So, we are going to talk about two-step forward. Okay, that's the first method, and also forward selection under marginality principle. Okay, and so we call them I-fort or I-form. Okay, I actually represents interaction, and then last year actually we decided to LASSO is so popular. Can we do actually LASSO, scalable LASSO actually for interaction selection? So here we actually studied another two methods. One is two-step LASSO, and the other one is like the regularization on the marginality principle for LASSO. We call it RAMP. Yeah, actually, original my talk title is based on RAMP. Okay, but I just modified the slides to make it more broad. So for each of these four methods, we can incorporate both strong heredities and also weak heredity conditions during the selection process. Okay. So here are just some notations. So we have a linear effects index M, interaction index I. We have these regression coefficients in three groups, and the design matrix X, and also X circle squared that actually is quadratic terms for X. Okay. And so first of all, I'm going to talk about the definition of importance. And it turns out if you look at the model, if you check whether this coefficient is 0 or not, that's not valid anymore, okay? Because this definition will violate the invariance principle. In other words, if you do a linear transformation on one of these variables, and the importance set can change, okay, based on the linear transformation you use. So we decide to actually correct this first. So first of all, we are going to give a new definition of important main effects. Okay. So if you want to claim xj is important, you need to check whether either it itself is important, it's important main effects, or it has important children. Okay. So even itself is not important as long as it has one important child, and that parent is claimed as important. Okay. So that's actually how we decide the important parents, main effects. For the interaction effect, it's still easy. It's same as before. Just to check the interaction coefficients to check whether it's 0 or not. So in this way, and our target are these two important sets, important main effects, okay, and basically important parents, and also important children. Okay. And so first of all, I'm going to talk about forward selection algorithm. So this is really a standard forward selection, and I think maybe everyone in this room know what you do for variable selection. So you have a lot of variables here. You pick one at a time and given the current model. So you have you put one in your basket at a time. You just check which variable will give you the most contribution to the current model, and you put that one in the model until the model is saturated, or until you don't see like a significant improvement in the procedure. So that's just a standard forward selection. And so we're going to actually first of all talk about how to do forward selection for interaction model. So this is actually a two-stage forward. Okay. So what we do, so first of all, at stage 1, you ignore the interactions. Just do standard forward for main effects only. Okay. And we know we can do this in our package, like lips, and you can do this. And then you will select a few important main effects. And at stage 2, you keep all these main effects, and also the children of those main effects in the model. So expand your candidate to important main effects and the children of those important main effects. And that is your current model. And then you do another forward selection. That's it, very simple. Okay. And then we can actually we can build this solution path for forward regression. Then we need to actually select the proper model size. In our work, we actually tried BIC and the different, BIC, AIC, and extended BIC. It turns out the best combination is at stage 1, you should use EBIC because your dimension is so high, and you want to reduce the dimension quickly. At stage 2, after you reduce dimension of the main effects already, you put their children. The model is already pretty at a moderate size. Then we suggest to do a standard BIC. It turns out this is the best combination. Okay, and then you may wonder, so is this procedure valid, and does it have a theoretical support? Actually, that has been a long issue in literature, and people actually have been trying to criticize this two-stage forward, because at stage 1, you ignore the interactions, only look at the main effects. So that model actually is misspecified. So we implement the forward selection on the wrong model, and how can you guarantee you will actually get the correct model structures? So that is true in general. So actually, and we can actually, so in this work, we're actually trying to find, okay, when this two-stage forward will work, okay? We're actually trying to find the conditions and when this method will work. It turns out it's pretty general condition, okay? So basically, we actually showed the I-forward, the two-stage forward, is screening consistent or short screening under some regularity conditions, and also under the assumption that the model follows a strong-headed condition. So if you look at these 4 conditions, like a normality for the X, and the covariance condition, and the signal strength, and the dimensionality. So all the 4 conditions here actually are comparable to when you deal with the main effects model only. Okay. So in other words, this is already almost as good as if you don't consider interactions. If you only look at the main effects selection problem, and that's also the conditions you need to do to make sure the model is screening consistency. And there's a slight difference. I'd like to point here. The slight difference is the condition C4 here. Okay, if you deal with the main effects, and this psi here will be smaller than 1. Okay, and so here, due to the interaction effects, okay, the psi here is a half. Basically, the dimension we can handle is actually smaller than the main effects only model. But that actually is quite expected due to the problem of large model. Okay, and so I'm not going to show the details. Everything in the paper basically we show that two-stage forward is screening consistency, screening consistent. Okay, and so you may wonder that the Gaussian assumption for X, can that condition be relaxed? Yes, the way we put a normality here is just for the just facilitate the proof, makes the proof easier. We actually can relax the Gaussian assumption to be sub-Gaussian, and also with the symmetric distribution, and also or sub-Gaussian with vanished third moments. So that's all condition those are weaker conditions we can use to establish this sign consistency. Screening consistency. Okay, so this is actually the first method. And then we notice there's some drawback of this two-stage method. Intuitively, one main drawback is that we select main effects first. Interaction come later. Okay, so we kind of feel like the interactions, if you have some strong interactions, they should go into model early. So we like to give that interactions some opportunities to get into the model early, and so we actually modify this I-forward by an I-form procedure. Okay, the main modification is quite simple. When you do forward selection, okay, you select one main effect at a time, but actually we allow whenever you select 2 important main effects, you add their children, their child to the candidate model right away, and so that they actually being selected early during the step process, during the selection step. Okay. So actually the major modification is we allow the interactions to be added to the candidate right after their parents are selected. Okay. So this actually is an iterative procedure. Okay. And so it's not a two-step, it's actually multiple step. You still add one main effect at a time, but you pick along their parents, their children along the path. Okay. So that's a kind of called I form. And on the similar conditions in the paper, we also show that this I form is a screening consistency, consistent. And based on our actually experiments, this I form works much better than the simple two-stage forward. Okay, 15. Okay, good. Okay, let's maybe, and also this can be, all this algorithm can be actually modified by replacing the strong heredity condition by weak heredity conditions. Okay. So now let's go to LASSO. And so for LASSO, I'm going to also talk about two-stage LASSO. Okay. Two-stage LASSO basically is like, we did not actually propose this. This two-stage LASSO was first mentioned by Efron in his last paper, and he talked about, actually, we can use LASSO or LARS to do the interactions selection in two stages. Okay, so stage one just simply solve the standard LASSO that identify the main effects, and stage two solve the expanded LASSO, okay, by including the children of those main effects selected at stage one in the model. And then when you solve LASSO, remember we have to force this hierarchical structure. So in order to do that, we only impose a penalty on the interaction effects. We are not going to penalize the parents, okay? Because we don't want the parents far out where their children stay in the model. So there is actually small modification here. The LASSO penalty only imposed to interactions instead of parents. So this is actually a very, very simple way of enforcing the hierarchical structure. You can just call last package twice, you can get it, okay? And so the computationally, it has huge advantages. People actually have been using this, particularly for the genetics studies, genetic data. They're trying to use it, but without any justification. Actually, if you look at the discussion paper of Lars, in the discussion, one actually author, Talarch, he put a counterexample to show that, okay, in some situations, this two-stage LASSO will not work, okay? It will not be screening consistency, okay? And in our paper, actually, we try to establish condition when the two-stage LASSO will work, and also try to explain why the Talarch counterexample is counterexample because it does not actually fall into our general condition. Actually, the example he gave is not, it's against the hierarchical condition. It's not even a hierarchical model, okay? It violates the heredity condition. So anyway, so we under some conditions, we actually showed the two-stage LASSO is sign consistency, and this actually is stronger than the two-stage forward. For two-stage forward, we can do screening consistency. Basically, we can capture the important terms, but at the same time, we may allow some noise variables into the model. But two-stage LASSO in theory is actually, it will get exact main effects without any false positive. Okay. And again, we need a normal assumption for X, and also two additional conditions. Actually, one additional condition is irrepresentative condition, irrepresentable condition. But this is really expected. But because for LASSO to be selection consistent, even for linear main effects only, we need this condition. Okay. So for interaction terms, we actually cannot really go away with this condition. Okay. And so in this paper, and we actually showed selection consistency for LASSO, and the theory essentially generalized the Wainwright 2009 paper for main effects model only paper. I mean, so it's really generalized that results to interaction effects. Okay. So basically, you just show that two-stage LASSO works in some situations, and then we realize, okay, this two-stage LASSO also actually suffers the same drawback of two-stage forward. The interaction going to the model is so late, and can we fix that? And the answer is yes. So actually, we developed an efficient algorithm to compute the LASSO path for this quadratic regression, and by enforcing its hierarchical structure to be held along the path. Okay, that's called a ramp algorithm. And for each, we apply CDA algorithm for each fixed tuning parameter to solve the problem. Okay, so essentially this actually is so this is CDA. So you have actually sequence of lambdas. For each lambda, we solve a LASSO, and we use the previous solution as a starting point, and we do we update the one coordinate one time cyclically until convergence as a CDA. And we actually just extended the CDA to interaction selection. Okay, so essentially we also solve these LASSO problems for a sequence of lambdas. And but remember, we have to make sure our hierarchical structure is preserved for each solution, and we do this by using two tricks. Okay, the first trick is like when we solve LASSO, we don't penalize all the parameters. For example, if a parent has children in the model, in the previous model, we're not going to penalize those parents. Okay, so we don't want to actually children in the model without parents. Okay, and second thing we do is when we solve this problem, sometimes you can pick interaction effects without parents, new interaction effects without parents, and whenever we notice that, we actually get their parent in the model right away. Because at each step, we actually check, okay, to make sure this hierarchical structure is preserved. Okay, so that's actually the whole algorithm. And we developed our package for doing this. It's really fast. It's essentially just in the same scale as a LARS. Okay. Yeah, maybe I give you a quick idea about how this ramp works. Okay. So this is actually a very simple two example. We have two main effects, x1, x6. I mean, the total dimension is 100, and the main important two main effects are x1 and x6, and the two important interaction effects are x1, x3, and x1, x6. And so this model actually does not obey this strong heredity condition, because the interaction x1, x3 only has one parent in the model, x1, x3 is not in the model. Okay, and so actually it follows this weak heredity. So we actually implement our ramp strong to this model, and also ramp W to this model. Okay, so let's look at how it works. Okay, so this is a ramp strong. So before we see the solution path, so in this actually we have four important predictors: x1, x6, the product x1, x3, x1, x6. The most important one actually is x1, x6. Okay, because its coefficient is high. If you look at the correlation, this one actually has the largest correlation with response y. If you ignore hierarchical structure, but it's a child. Okay, so it cannot be selected at first. So let's see. So this is the path for the ramp strong heredity. So first of all, it selects x6. Okay, the first parent x6 in the model. Then next one is x1. Okay. Then after this, both parents are in the model. The strongest predictor x1, x6 get into model. Okay. If you look at this path, there is another strong interaction x1, x3. It actually does not get into the model at early stage. Okay, because that x1, x3, its parents x3 is never selected. So the children actually is left out until very, very late. Okay. So that's actually the path for the ramp strong. And so this is a path for the ramp weak. Okay. This, as I mentioned, this model actually follows the weak heredity condition. So the ramp weak, select x6 first, then immediately the child x1, x6 kicks into the model, okay, even before the parents x1 in the model. Then next one is x1, and then next one is x1, x3. So let's look at the path, okay. So x6 enters the model, then its child x1, x6 enter the model, then x1 get in the model, then the child x1, x3 in the model. So this ramp weak identify all these important main effects and the children in the proper order. It does not leave out one. It does not leave any important terms. Okay. I have 5 minutes. I can talk about quickly talk about the numerical studies. So you may wonder how fast this one, the ramp. Actually, it's now available in R, so you can just download it and try it. Let me give you an idea. If you have a 400 sample size, dimension is like 10,000 variables. It takes about less than 30 seconds to get the whole solution path. Okay, and also right now, we actually you can try different heredity conditions, strong or weak. And besides LASSO, you can also try SCAD and MCP or different penalties. And also we actually generalize this procedure from linear regression model to quadratic to generalized models. Okay. So here is like how to extend this to generalized quadratic regression models. So naturally we just use a link function and deal with penalized likelihood estimator. I'm not going to talk about those. So everything follows actually in a similar way. You just replace the loss function, replace the least square loss by likelihood loss. Okay. I give you a quick comparison of these 4 different methods: iFort, iForm, LASSO, and ramp. Okay. So you may wonder which performs best. And so this is actually, here are the first 2 examples. So here example 1, dimension is 5,000. Okay, I have 10 important main effects, 10 important interactions. And example 2, we further push this dimension to 10,000. Okay, and the sample size is the same, 400. It's much smaller than dimensionality. Okay, and we report the accuracy of identify correct interactions, main effects, and also we check the prediction error. Okay, so you look at here. So maybe let's just focus on this. So when sigma equal to 2, we try different signal noise ratios. So if you look at it here, so you can see the best accuracy for identifying interaction is iForm, which is forward selection with marginality principle, and the ramp. Okay, that is our solution path. And if you look at all of this, so overall we actually observe that the ramp works basically the best, followed by iForm. So it turns out that simple 2-stage actually can be further improved by using this hierarchical search. So I have 3 minutes. Okay. If you wonder, the computation time for the forward regression-based method, they are also pretty fast. So here is the computation time. When we increase dimension nality from 500 to 5,000 to 10,000, it's a 2-stage forward. It's roughly like less than 30 seconds, and also iForm, it's similar scale. Okay, so it's pretty fast. And then actually, there's also one example to show logistic regression with a binary response. So here we actually compare the ramp with the 2-stage LASSO, 2-stage SCAD, and Oracle procedures. Okay, we'll also try different settings. So let me just give you, so simply speaking, when signal is strong, ramp, 2 LASSO, 2 SCAD, they all work pretty similarly. But when signal is weak, so here beta 1 is 1, that actually is the smallest regression coefficient. then we have beta 1 equal to 2 and 3. When signal is weak, we notice ramp outperforms the two-stage lasso and the two-stage SCAD in terms of interaction and also prediction. You can see ramp, the prediction error actually is the smallest amount is 3. The last row, that is Oracle procedure. Okay, so we actually we have tried to apply this techniques to real data. The first real data we tried is the supermarket data, where we were to try to find the predict the number of customers in a supermarket, and the sample size is 400, and the dimension of the data is about 6,000. Okay, and we tried ramp and compared with LASSO, and for the ramp we actually tried the different tuning procedures: AIC, BIC, EBIC, GIC. Okay, so basically, the way that we actually see that is, so overall speaking, ramp works better than LASSO, and if you use a very like a stringent tuning parameter criteria like EBIC, GIC, which falls smaller sparsity, the ramp performs much better than LASSO. And for example, with GIC, ramp select 30 variables, okay, and the R square, outsample R square is much higher than the LASSO, okay. And also, we tried forward selection method, and overall speaking, ramp based on LASSO method, which works best among all the 4. This is the last slide, and we apply this to the microarray gene expression data, and which has 60 arrays, then total dimensionality, total number of genes, it's actually 22,000 or something, and we actually use some feature screening procedure. And we actually did a pre-selection and selected about 1,800 genes. Okay. Now we applied these procedures. We identified some important genes and some important gene-gene interactions. Okay. In this paper, actually, when we revise the paper, we are asked why you pre-selected genes. Can you apply your procedure to these 22,000 genes directly? And we also did that in the paper. And so, right now we are actually trying to implement LASSO-based method to this gene expression data. Okay. So summary. So basically, we have proposed scalable algorithms with complexity linear in P, and also provide some theoretical insights for two-stage forward and two-stage LASSO. And lastly, I want you to remember the ramp package and try to download it today and try it on your data. Okay. So here are the papers I just mentioned in this past 3 years. Okay. Yeah. So that's all. Thank you.
So one quick question.
In your earlier theory, you said that you require the strong hereditary assumptions. But then you also mentioned the weak hereditary assumptions. So do you also have a theory for the case when you just have weak hereditary, or are you just saying that your method seems to work well in those cases?
Yeah, in our paper, we did not really study the theoretical property for weak heredity conditions. It's possible. We just focus on strong heredity conditions. Yeah, thanks. And there is some actually work on which ignores, which do not believe the model hierarchy assumptions. It's just the same. It's impossible that you only have important children without parents. So I mentioned the paper by Feng. He has a paper on sure screening for interactions, only selecting interactions by ignoring parents. So actually, it's really a philosophy issue whether you believe the model should follow this hierarchical structure or not. Yeah, thanks.